Episode 8 of Overview Biostatistics is very important. We will now touch the method called statistical inference. We rely this method on what always true, which is the distribution of sampling mean, which always follow the normal distributions if the sample size is large enough. Then take an example of one study. Let's say we collect the data about weight of 25 people, and then we have the weight of 25 number, and then add all number, we get the summation divided by 25, we get the mean of 52, and calculate for standard deviations which equal to 5. If this raw data are distributed normally, we can put the number in here, but we cannot rely on this. That is why we cannot use the property of normal distributions to this raw data set. But we will rely on the row number T3 here, the distributions of the sampling mean. Now, what we aim for is to get two things for the statistical inference. The first one is parameter estimations to get the 95% confidence interval of the mean weight that would be found in the population, and test the hypothesis. Start with this. So in the third row, where it follows the normal distribution, we really need two parameters here. The first one is x bar of the x bar and the standard error to be able to use the normal distribution properties. But we have done only one sample with the sample size of 25, not repeated sample to get x bar of the x bar. What we need to assume here is that we will take x bar from only one study as if we get x bar of the x bar. Okay, it makes sense because we cannot use x bar for the purpose of using SD of the raw data. But we have no choice rather than x bar to assume to be x bar of the x bar. Only the best choice. And the data at hand, we have only that. And how about the standard error? Because we do not have many x bar to calculate for standard deviations of the x bar, or SE. Then we calculate by this formula that the standard error equal to standard deviation divided by square root n. So it is equal to 1 because 5 as standard deviation divided by the square root n is 25. So now that means we will follow this because we already have the two parameters. From one study sample, from one study with sample size of 25. The first one we will do is to estimate what would be about the weight, the mean weight in the population. So we calculate for the confidence interval, and here is the general formula it's come from the statistics obtained from the study sample of 25 plus or minus something. So it will be a range plus or minus, mean lower and upper limit of the interval. That thing comprise the coefficients that correspond to the percentage here. That's what we want. If we want 95% sharply, okay, it will correspond to what? To the coefficients. If sharply exactly 2, it's 95% 0.45. But now we don't take 0.45, 95% 0.45. We just take 95% only to get the 95% CI. It will not be 2. It will be less, a little bit than 2 because 0.45 here. And that is the number of 1.96 correspond to 95%. So that's the coefficient. Therefore, if we want to have 99% confidence interval, we will take the value of up to here, not 0.73, but 2 point something, right? Not touch 3. Okay. So then we multiply by the standard error or the distributions of the sampling mean in this case. So which is 1. Then we substitute this to the general formula. 52 is the statistics obtained from the sample, plus or minus this one, and then multiply by the standard error. And here is the answer. We say that we are 95% confident that the population mean would lie between 50.04 to 53.96, or about 50 to 54 approximately. And that's it. Easy, right? Every statistics fall into the same concept. Whatever the statistics is, you could change from mean to proportions to the ratio like relative risk ratio, odds ratio, hazard ratio, whatever. The same way. The difference is this thing, the standard error. Okay, you calculate for that statistic plus or minus the coefficients. The coefficients remain the same. Okay. So here is the first component of statistical inference, parameter estimation. Now, the question is that what could affect the width of the confidence interval? This is very important. We need to understand about this, because if the confidence interval is narrow, we call it precise estimate and tend to have a conclusive finding. Means we can conclude things in the conclusions. If the width of the confidence interval is wide, that means imprecise estimate and tend to be inconclusive, or we know nothing from doing the research. So it's a waste of time. Therefore, we will plan to have a precise estimate. Then, how can we get that? So we need to understand about that. What affect the width of the CI. For this purpose, I bring you to this writing whiteboard. Suppose we have this, and this one affect the width of the confidence interval, right? What we can do is we can change these two things. The first one, if we change the confidence interval for this purpose, if I want the 99% CI, it would be 52 plus minus 2.58 multiplied by 1. Okay. So it will be wider, right? Wider. So of course it will be more confidence because the confidence interval is wide. We are 99% sure because it will cover the truth, the true mu, the true parameters for sure because it's wide. But as I said, the wider the confidence interval, the less informative we can get, or it tends to be inconclusive. So there is no benefit by increasing this confidence interval coefficients. Then what next? What we can play with is the standard error. We will not play with this to get a precise estimate. So how can we deal with the SE? Since we know the SE or standard error come from the SD divided by square root n. This is the magnitude of variation. We cannot do anything with this because this is the nature of that data, the variability of it. If it is wide, high variations, it's always high. We cannot change it. But this is what we can do. So if we want a precise estimate, we need to increase the sample size to get a precise estimate. The larger the sample size, the narrower the confidence interval, and tend to get a conclusive findings. Now back to the slide and proceed to the second component of statistical inference, which is the hypothesis testing. For the hypothesis testing, this is the general formula. We get the statistics from the study sample, take the difference from the null value. The null value specified under the hypothesis, the null hypothesis or H0, divided by the standard error. So it just quantify the number of times of the standard errors that the statistic differ from the null value. In here, what we need to have in this component is we need to know about the hypothesis being tested. So null hypothesis or H0 here is the hypothesis of no difference. Since we have just only one sample, no comparison. So I just make it up that if we have a research question that if the weight of this group differ from 55 kilogram or not. Okay, so here is the hypothesis. The noun will be equal to 55. The alternative put this that not equal to, this is called two-sided hypothesis testing. Okay, so this just make it up. But if in situations where we have the comparison group, so we will have mu1 equal to mu2 or mu1 minus mu2 equal 0 as the hypothesis. No need to make it up. So this is a standard value. I just make it up for this demonstration purpose. So we substitute the number that 55, the noun, minus 52. It doesn't matter to take which one come first, and divided by standard error 1. So it is 3, and then this is correspond to number of times of the standard error, right? 3 correspond to this area, the area that is unlikely. Okay, so it's in the tail of this. Then the area of this correspond to what? To 1, the whole area is 100% or 1 probability, minus this one, which is 0.9973, because it's correspond to 3. It's equal to this probability. This is the p-value. It's equal to 0.003 approximately, or 3 out of 1,000, right? And here is the interpretation. We repeat the null hypothesis first. If the true mean in the population is 55, think about that. Is there a chance that even the true mean is 55, is there a chance that one survey of weight with the sample size of 25 to get the mean weight of 52? Of course, the answer is yes. There is a possibility to get that, a chance to get that. The probability here is not about the chance to get that, but the chance to get that value or more extreme than that. That means go into the other ends. So here is the direct interpretations of p-value. Repeat the null hypothesis and then say the probability or the chance to attain the sampling mean of 52 or more extreme is equal to this. What is it really mean? It's really just mean that it is very unlikely to get the sampling mean of this, or higher or lower in this case. That means or lower. With what is that probability? About it's very small probability. It's about 0.0027. What does it mean? It means that it's very rare chance. Then we can say it's what we found belong to another population, not the population with the mu of 55. Okay. So with this difficulty of understanding, people ask about how small that is small. So somebody set a rules about less than 0.05. And then what we can say? Significant. Okay. So if it's less than that, this means very small chance. We say it's significant and turns this sentence to be the mean weight is significantly differ from 55. That's shorter. But it's really, really misleading to be a lot different. Okay, we can take a closer look at this about what affect the p-value as against the magnitude of effect in here is about the difference between the statistics and the parameter mu. Let's take a look in that webboard. Okay, so with this example, we have the answer about p equal to 0.003. We usually report the p-value of 3 digits, 3 decimal digit. Or in short, people say it significantly differ from 55. Now, if I change this to 2 scenarios, the first scenario, I will just change the n to be very small n, like 4. Everything is the same, means that the x bar equal to 52 and the SE equal to 1. Now just change the sample size from 25 to 4. This one give the p-value of 0.003, right? Now, what is the answer here? P-value of what? We just make a simple calculation, so it's 55 minus 52, which is the statistics and the null value, divided by standard error, right? The standard error here, sorry, it is when the sample size is 4, the standard error no longer to be 1 anymore. We will calculate for this by what? By the SD still remain the same, right? SD equal to 5, n equal to 1, so it's 5 divided by square root n equal to 4, square root 4. So here is about 2.5, right? So it's 2.5. Okay, so it is 3 kilogram difference divided by 2.5 from here. So it's equal to 1 point something. 1 point something, it will be around here. You know, if 1, it will be 68.26, but point something is around here. So I just make it up for a quick tour of this. Larger than 1 a little bit. So let's say it's 70% of this area. Therefore, the p-value rather than 0.003 here, it then increased to be 0.3 something, right? Because 1 here, 1 in this is correspond to about 68. 1 point something, I just make it up to be larger than that, so make it easy. 70%. So the remaining here will correspond to 1 minus 70. 0.7, so it's 0.3. Then the conclusion will change from significance. The result change from the significant finding to non-significance, you see. Therefore, in this scenario, I just demonstrate that everything the same magnitude of difference of the mean 3 kilogram, the same standard deviations of 5, but change only the sample size. If the sample size is small, the p-value will be increased. You see that? So from significance to be non-significance. What does it mean here? It means it's a high probability to get the results like that in the sample size of 4. It doesn't mean it non-significant doesn't mean it's no difference. It's the same, 3 kilogram difference. But the probability of obtaining this is highly likely. Just that. But we cannot say it's differ or not differ. Let's go further to change to the very large study, like 10,000 sample size. But now I will change the x bar to make it very close to the null. So let's make it like 54.5. And we need to calculate for SE, right? SE then equal to 5 standard deviation divided by square root of 10,000. So it's 5 divided by 100. Right? So the SE is 0.05, very small standard error, because the large sample size will have the sampling mean that is close to each other. Okay, then we calculate for the p-value. It is what? 55 kilogram minus 54.5 from here. The difference is just half a kilo, 0.5 kilogram. Divided by what? Divided by 0, the standard error here, 0.05. It's about 10. Right? So 10 correspond to very far away from 3 here. So that means the p-value would say something like p-value equal to 0.00000 something. Okay, so it's very small probability, and say like very highly significant. In some journal they put the star like this to designate the significant findings, as if it's a hotel. Okay. So the second scenario tells us that even if the magnitude of effect that differ are very small, like half a kilo, we can get the significance findings if the sample size is very, very large. So the p-value did not correspond to anything about the size of the magnitude. That is the second component of the statistical inference. I like to emphasize here about these two components. report and interpret p-value appropriately. How? So the example of over-reliance on p-value, do not do like this. For example, real results is very large sample size like that, and the odds ratio compare treatment efficacy between drug A and drug B equal to 1.02. The ratios of 1 is the same thing divided by the same thing. That means the efficacy of drug is almost the same. But it can significant if the sample size is large. So in this scenario, if we report like it is less than 0.5, or sometimes put the star or 4 star like that to indicate the significant finding, this will make the audience misleading the what's happened to my English? Misleaded to understand that it's differ significantly. I mean, or the efficacy drug A is more efficacious than drug B, for example. It's mislead the people, because you see the magnitude of effect is very small, but p-value is significant. So if put like this, that means we mislead people. It will be wrong if say that drug A is highly significantly better than drug B, because it doesn't better. It's just 1.02, it's just close to 1. 1 means nothing. The same thing, the same efficacy. So sometimes the confidence interval of like this very wide, you know, from 1 touch something that no different is the same to 1.3. If the confidence interval of 1.02, you know, this one is just from the statistics. This one is what would be found in the populations or the confidence interval. That means in the lower limit tell us that there are no different. In the upper limit tell us that a difference is about 30%. So if 30% is not meaningful according to the information about drug A, which is, for example, if very expensive and hard to store, for example, even the upper limit tell us that there is no benefit at all. So even its significance, but the conclusion is actually no clinical meaningful. All right. So we will not interpret it based on the p-value, but the parameter estimations. Here in this example is the odds ratio. Second, over-reliance on p-value. If the real results like this, the smaller sample size, it's have a very high odds ratio, like 9 times, but the p-value is non-significant. What does it mean here? If we quote the p-value of this, no significance, and say there is no statistical significant difference of the treatment effect, and put the p-value there and interpret that drug A is as effective as drug B. This will totally wrong, because it's show us that it's 9 times the efficacy of drug A compared to drug B. But just sample size is small, it cannot detect significant findings. So if we say like this, it's wrong. If the sample size like this, the confidence interval will be wide like that. It's less than 1, and that means protective a little bit, or close to 1, not nothing. And there's upper limit, that means it's very high efficacy compared to duck B. So this is inconclusive. That means this study is in fact with the non-significance in low power. It doesn't suggest about no significant and then no different or equivalent. It's really differ a lot, but there is low power. Cannot detect the significance findings. We can just say that there was no sufficient information to conclude that based on the alternative hypothesis, say duck A is better than duck B. We cannot conclude like that. Or sometimes we say inconclusive findings. Or some people say our knowledge before and after the study is the same. So that's a useless study. So that's something that I like to inform you about this p-value. The p-value is not the magnitude of effect. P, probability, is the magnitude of chance. So p-value of 0 less than 0.05, we just say significance findings for easily or short, but actually we need to say in a full details, a full meanings of it. What it means is there is a small chance of being wrong in rejecting the null hypothesis. The more accurate one is we repeat the null hypothesis in the first place. Like if in fact there is no efficacy, no effect, no different and whatever, it is unlikely, when significance unlikely, it means p-value is small, it is unlikely to get the effect from the statistics of that magnitude, like 52 kilograms, something like that in our example, or more extreme. Okay, so this is the correct interpretations, but people difficult to get that, so they just want to hear a very short and simple things, and then it's misleading. So significance in this doesn't mean it's important. Any extra large study, a mega study, can give a very small p and everything is significance, even if the magnitude of effect is very, very small. In the opposite, if non-significance finding, we can just say that there is a high chance of being wrong in rejecting the null hypothesis, and it will be safe if we repeat the null hypothesis in the first place and say something like, if there is no effect, the chance to get this is still high. So non-significance does not mean difference, equal, no association, no difference, It does not mean that. It's did not related to magnitude of effect. Any small study can give a very large p-value because the standard error is high. Even if the magnitude of effect is very large, it's still non-significant if the sample size is not enough. Therefore, we cannot rely on this p-value for the interpretations of most of medical research. So be careful about that.